Good morning. Today we're going to do chapter 10, part 2. So only one more part after this and then we're done. Yay. All right. So remember last time we talked about the ideal gas law, and now we're going to talk about standard conditions, except these are similar to the standard conditions of chapter 9, that little degree sign, but now we're going to call them STP for standard temperature and pressure. Okay, so standard temperature is going to be 273 Kelvin or 0 Celsius. Standard pressure is going to be 1 atmosphere. Of course, standard moles is 1 mole. This one is also new. At STP, we've got 22.4 liters. And that number comes from, if you plug in all the values of standard conditions into the ideal gas law, you get 22.4 liters. Okay, and this is called the molar volume at STP because it's equal to 1 mole. This is important. 1 mole is its molar volume at STP, 22.4. Super important, equals 1 mole. All right. Okay, so that molar volume at STP, just remember that a mole is equal to 6.02 times 10 to the 23 particles. And so a mole of any gas at STP is going to occupy that 22.4 liters because a mole is a standard value. All right, so there's that. A mole is equal to 22.4 liters at STP. Just remember, density is grams per liter. So if we're doing molar density, we're doing molar mass divided by molar volume, which is that. So this bottom would be 22.4 liters. So the molar mass would just come from the periodic table. So if I needed the molar density of helium, it'd be 4 divided by 22.4. If I needed it for nitrogen, it'd be 28.02 divided by 22.4. Okay, also remember molar mass is equal to mass divided by moles. That's what we split molar mass into as a conversion factor, grams and moles. So just remember that. It's not too bad. And then this M is going to be molar mass. Sometimes the M looks like a normal capital M. Sometimes it looks kind of cursive-y looking. So just be aware. Here we're just deriving the gas density equation from the ideal gas law. They're going through, doing all the math. This is our density equation that's directly proportional to molar mass. So the pressure times the molar mass over the R value times the temperature. Remember that temperature needs to be in Kelvin. Okay, so here's that more cursive molar mass. This is exactly what I was talking about, but just remember, if you see that capital M in this chapter, that's what they're talking about, molar mass. All right, so let's calculate the density. Okay, so our density equation is P times the molar mass over RT. Don't forget, our pressure needs to be in atmosphere, so I need to divide 755 by 760. I get 0.993. It asks of nitrogen. Remember, nitrogen is diatomic, so it's 28.02 grams per mole over R, 0.0821 liter. Sorry, that's not 373, that's 398 Kelvin. Okay, so the reason this comes out to grams per liter, our kelvins cancel, our atmospheres cancel, our moles cancel, and I get grams per liter left. I get 0.852 grams per liter. All right, let's do one more. Let's do the 4 more practice 10.7 because this one wants us to calculate molar mass. So it's going to give us our density. So I've got 1.43 grams per liter equals 0.789 times the molar mass over 0.0821. And then 23, it'd be 296 Kelvin. All right, so this is a cross multiply situation. I get that the molar mass is 44.0 grams per mole. Okay, and sometimes it's going to ask you what that is. So you could speculate. Some people would go to the periodic table, look for 44. Well, that's scandium. This is probably not scandium because it's a gas. So if I had to guess, remember carbon dioxide is 44, I would say this was carbon dioxide. Now in this specific question, it didn't ask us to do that, but sometimes it does. All right, here's another molar mass problem. Oh, but this one gives us mass and volume. Okay, so I would say on this one, we're going to do the molar mass is equal to grams per mole. So I need to solve moles. The reason I'm doing that is because that last density equation we were using doesn't have liters, but this problem does. So I'm going to go with the premise of I need to use PV equals nRT to find moles and then plug moles into that equation. So I've got, don't forget to convert your millimeters of mercury to atmospheres. Okay, I'm going to do that times my liters divided by 0.0821 divided by 328. I get that N is 0.00974 moles. So I do 0.311 divided by that. I get molar mass is equal to 31.9 grams per mole. .9. Yes, it's reasonable. Okay, this one is the same process, but it's just milligrams, so you need to convert that to grams before you did the problem. All right, so next up is mixtures of gases. So as you know, air is a mixture, and we talked about that when we did chapter 1, when we did classifying matter. So just remember, most of air is not oxygen. Most of it is nitrogen, and that balance is very important. Okay, so Dalton's law is the one that talked about partial pressures. He states that the total pressure of a gas is the sum of the partial pressures, and the particles have negligible size and do not interact. That is very important. Remember, the average kinetic energy is the same, which means the total pressure of the collisions is the same. So Dalton's law of partial pressure is us just adding up the pressures down here of each of the pieces to equal the total. Sometimes we use the ideal gas law for this. We solve for pressure, and it's the pressure of a specific type of gas. And then when we use that gas, we can add it to the other ones. So here you can see we're adding this piece and this piece and this piece in. We found all of the ideal gas pressures, and then we solve the Dalton's law of partial pressure. Okay, we can also get mole fractions from this. So a mole fraction is the part of the mole over the total moles in the mixture. And then to get a partial pressure, we can multiply that mole fraction by the total. Okay, so if we know I have 0.78, that's my mole fraction, and my total is 1, that means I have 0.78 atmospheres of that nitrogen pressure. All right, so here we go. We've got volume, pressure, temperature, pressure, what's the mass of argon present in the mixture? Okay, so has a total pressure of 66.2 millimeters of mercury. If the partial pressure of helium is 3.41, the partial pressure of neon is that, and we also have argon. Okay, so it doesn't really matter to me which way you do this, but we are going to need an ideal gas law to get moles out of this. Okay, so if it were me, remember it's P total equals P1 plus P2 plus P3 plus dot, dot, dot. Okay, so my total is 662. My pressure 1 is 341. My pressure 2 is 112. And my pressure 3 is unknown. So I would go ahead and solve for pressure 3. Okay, and I get that pressure 3 is 209. So at this point, we could plug that into the PV equals nRT equation. The ideal gas law, don't forget to get it to atmosphere, so I get 0.275 atmospheres times 1 liter equals, I don't know moles, I get that N is 0.112 moles, and then I take that number, I'm going to multiply it by the mass of argon, 39.95. I get 0.449 grams. All right. And there they did it the exact same way. Okay. This one has our mixture has a total pressure of 755. Water has a pressure of 24. And then we've got, we want to know the amount of hydrogen gas. Okay, so we do 755 torr equals 24 torr plus P, and I'm going to put H2. So then I'm going to do 755 minus 24. Okay, don't forget to convert that to atmospheres. So I get 0.962 atmospheres times 1.55 liters equals N times 0.0821 liter atmospheres per mole Kelvin times 298. I get that moles is 0.0609, And I'm going to times it by 2.02 grams per mole. So that's the mass of hydrogen. I get 12.3 grams H2. Okay. So the next thing we're going to talk about is the partial pressure while diving. So these are the same percentages of the atmosphere that we see on the surface. The 78% of nitrogen, the 21% oxygen, and the rest of other things. So when you're diving, scuba divers do want to make sure that their oxygen percentages stay the same. Okay, so as you dive, like here it's 4 times the amount because they went 30 meters deep. Remember, it changes by 1 atmosphere every meter. So they want to make sure those percentages stay the same. So here I've got 12.5 liters, 24.2 grams of helium, 4.32 grams of oxygen at this 298. Calculate the mole fraction and partial pressure of each component in the mixture and the total pressure of the mixture. Okay, so the first thing we need to do is find moles of both helium and oxygen to get our mole fraction. Okay, so 24.2 grams of helium. Excuse me. Helium is 4.0, just 4. This is 4.00. 4 grams helium. And I'm going to do 4.32 grams oxygen. Just 32 grams of oxygen. 1 more. Okay. I've got 6.05. 0.135. So the mole fraction for helium is going to be 6.05 over 6.185. .978, and then the mole fraction for O2 is going to be 0.135. .0218. All right, so there are mole fractions. Remember, it's just part over whole. We don't do times 100, but these are specifically in moles. Okay, and then we want the partial pressure of each mixture. But first, we also need the total pressure. Okay, so if it were me, I would find the total pressure first. And you can do that by adding, well, using the total moles in the PV equals nRT equation. So P times 12.5 liters is equal to the total moles of 6.185 times 0.0821 times 298. I get the total pressure is 12.1 atmospheres. So at that point, I'm going to go ahead and box these in. To find the partial pressure, so P of helium is 0.978 times 12.1. I get 11.8. And then for oxygen, I get 0.0218 times 12.1, and I get 0.264. Okay, and to make sure at the end those are equal, we could add them back. And it rounds to 12.1. So we're good. Okay, 0.264, that's what we have, 11.8. We have 12.1 for our total, and our mole fractions are good. Okay, we've got mole fractions, we've got a partial pressure of oxygen. Okay, the oxygen mole fraction of 0.05. What's the total pressure if the partial pressure for oxygen? So remember, P total is equal to X of, in this case, oxygen times P of oxygen. Sorry, that's wrong. P total's over here. Yeah, there we go. That looks better. Okay, so I need to switch my P total and mole fraction, or my oxygen pressure spots. So P total is equal to partial of oxygen over that mole fraction. All right, so I've got 0.21 atmospheres times 0.05. And I get P total, it's 4.2 atmospheres. So it's just a matter of manipulating the equation with algebra. It's not too bad. All right. I believe this is the last major topic of this video is vapor pressure. Okay, so gases are often collected by having them displace water from a container. Okay, and that the problem is there's also a water vapor that we need to keep into mind. And the partial pressure of the water vapor is called vapor pressure. And the only thing vapor pressure depends on is temperature. So at different temperatures, the vapor pressure is different. And here we can see, again, this is in Celsius. Remember, all calculations need to be in Kelvin. But this is that one we normally use, the 23.78 millimeters of mercury. That's about room temperature, 25 Celsius. And then they go up from there. So here we have, in order to determine the rate of photosynthesis, oxygen gas emitted by an aquatic plant is collected over water at a temperature of 293 Kelvin, which is at 20 degrees Celsius. And the total pressure it gives us is 755.2 millimeters of mercury over a period of time. A total of 1.02 liters is collected. What is the mass in the form of grams? All right, so we do need the pressure here is 17.55 millimeters of mercury that we needed to subtract from that initial value of that 755. This is our partial pressure of oxygen here. That doesn't include the water vapor. And then we just do an ideal gas law, and then we convert to mass. Okay, so it's similar to what we were doing before. It's just the vapor pressures have a specific table. The water vapors have a specific table that you look at based on the temperature. Okay, so this one, we're starting at 742. We look at that 25, which I think is the 23.7. We would subtract them, and we would go through the same process that we just did. All right, that's it for the day. Y'all have a great day.